Hey guys, so we're going to talk about section 1.6 today, which is other types of equations. Section 1.5 was all over quadratic equations, which is a very specific type of equation. And so today we're going to broaden our horizon a little bit and talk about others. So the first type of equation we're going to talk about is called a polynomial equation. And actually, you've already done things with this. Most of your mathematical career is using polynomial equations. Those are quadratic equations and those are linear equations and things like that. So a polynomial equation is simply where two polynomials equal each other. So a polynomial is a single term or the sum of two or more terms that contain the variables with whole number exponents. That's like the special rule, is the exponents have to be whole numbers. You don't get fraction exponents with polynomial equations. We'll talk about that in a little bit with rational equations. So they have to have whole number exponents, and you have to set them equal to each other. In general form, our polynomial equations have to be equal to 0, and then the left-hand side is in descending order. That means we have like x squared plus x plus our c equals 0. Our quadratic equations are written in that form, and that helps us to factor them and to solve for the variable. And that's why it's important to get them in general form. The degree of a polynomial equation is simply the highest degree of any of its terms. So with our quadratic equations, all of them had an x squared, so they're all called second degree polynomials. It's not super important that you know the degrees of the polynomials. Like, that doesn't really come into play very much, except that it's nice to understand how you get that information. So here's a couple examples of some polynomial equations. We have 3x plus 5 equals 14. This is a first degree polynomial because we just have an x, and if there's no variable, or if there's no exponent above the variable, then we understand that to just be an exponent of 1. So we would say this is a first degree polynomial, and it is not in general form because look, we have this 14 on the right hand side. So it's not equal to 0, so it would not be in general form. The next one, we have 2x squared plus 7x minus 4 equals 0. This is a second degree polynomial. Notice that we have an exponent of 2. That's the highest exponent, so it's a second degree polynomial. And it is in general form because we go x squared, and then we have an x, and then we have just our whole number. So it's in descending order based on the exponents, and it's set equal to 0. So that is in general form. This last example, we have x squared plus 3x to the third equals 4 plus 4x. Now, even though our first term is x squared, we would call this a third degree polynomial because the highest exponent is 3. Now, this is also not in general form because it's not in descending order and everything is on both sides, so it's not equal to 0. So that is not in general form. But that gives you some examples of what polynomial equations look like. And we spent all of 1.5 on quadratics or second degree polynomials. And so today we're going to branch out and do third degrees and above. So the first type of problem we're going to do is this, where we have 3x to the fourth equals 27x squared. We're going to solve this by factoring, but it's not factoring like we did with quadratics where we have parentheses times parentheses because we don't have 3 terms. We only have 2 terms. So the first thing you want to do though is you want to get it in general form. So I want to get my 27x squared and I want to move it over. So I'm going to subtract it. So I get 3x to the fourth minus 27x squared equals 0. Once I have it equal to 0, and since I only have 2 terms, I'm going to look at those 2 terms and I'm going to ask, what do those 2 terms have in common? Do they have anything in common? Well, does 3 and 27 have anything in common? Yes, they have a 3. And then what about x to the fourth and x squared? Well, they have an x squared. Whoops. So I can take out a 3x squared. So 3x squared times what gives me 3x to the fourth? Well, x squared. And 3x squared times what gives me a minus 27x squared? Well, that'd be a minus 9. Remember, when you do factoring by pulling out what they have in common, you're basically doing the reverse of your distribution property. So when we distribute our 3x squared inside of our parentheses, we should get right back up to our original problem, which we do. Now, once we have 3x squared times x squared minus 9, we have our zero product principle, which says that if we have a times b and that equals 0, then either a equals 0 or b equals 0. So what that means is we can set each of these equal to 0 and solve for our x. So we have 3x squared equals 0, and we have x squared minus 9 equals 0. So to get x by itself, I'm looking at just this left equation right now. I'm going to divide both sides by 3. 0 divided by anything is 0. To get rid of the square, I have to square root. But if I square root the left, I have to square root the right. So I get x equals 0. Now look at x squared minus 9 equals 0. I'm going to add 9 to both sides. I need to get rid of that squared, so I'm going to square root both sides. So x equals, well, what is the square root of 9? You're probably saying 3, and that's not totally wrong, but it's also not totally right. Because when you take the square root of 9, you get plus or minus 3. Because 3 times 3 gives you positive 9, and negative 3 times negative 3 also gives you positive 9. So for this problem, our solution set would be negative 3, 0, and 3. Those are the three solutions that we got. We got 0, negative 3, and positive 3. Okay, let's go work another one. That was factoring by pulling out what they had in common. We only had 2 terms. So for this problem, we're going to have 4 terms. We have x to the third plus x squared equals 4x plus 4. I'll scroll down in my notes so that you can see at least the start of the problem. I don't want to give away all the answers. Okay, so if we're solving this equation, we need to get everything on the same side of the equation. So I'm going to move everything over to the left side. I'm going to subtract my 4x and I'm going to subtract my 4. So I get x to the third plus x squared minus 4x minus 4 equals 0. I get everything moved over to the same side, and I get it in descending order, so I'm putting it in the general form. And then what I'm going to do is I can't factor it like we did quadratics because there's 4 terms instead of 3. I can't pull out exactly because not everything has anything in common. So this form of factoring is called factor by grouping. And what we do then is we're just going to look at the first 2 terms. And we're going to say, what do they have in common? What does x to the third and x have in common? Well, they have an x squared. X squared times x will give me x to the third, and x squared times 1 will give me my x squared. Now I'm going to look at my negative 4x minus 4, and I'm going to ask the same question. What do they have in common? Well, they have negative 4 in common. Negative 4 times x gives me negative 4x. Negative 4 times 1 gives me my negative 4. Here is the whole goal of factoring by grouping. When you factor by grouping, notice we have a term times a parenthesis minus the term times a parenthesis. What is in our parentheses needs to be the same thing. If it is not, then we didn't factor by grouping correctly. So over here, when I pulled out minus 4, let's say you didn't pull out minus 4 and you just pulled out a positive 4. You would have had a minus x minus 1 inside your parenthesis, which doesn't match. So hopefully at that point you could say, well, they both have a minus, so let me pull that out and see if I get the right thing inside. and you would. So we now have x squared times x plus 1 minus 4 times x plus 1. Now we can pull out that x plus 1 because this term has an x plus 1 and this term has an x plus 1. So I can pull out the x plus 1, and that's going to leave me with what's out front. What's out front is now going to go in my second parenthesis. So that'll be x squared minus 4. So I pull out my x plus 1, and that leaves me with x squared minus 4 to go in my second parenthesis. Now I have the zero product principle again. I have something times something equals 0. So my something equals 0 or my other something equals 0. So I can set each of my terms equal to 0. So I have x plus 1 equals 0. And I have x squared minus 4 equals 0. Subtract 1 to both sides, and I get x equals negative 1. Add 4 to both sides, and I get x squared equals 4. Square root to get rid of my square, and I get x equals plus or minus 2. So then my solution set is negative 2, negative 1, and 2. The biggest mistake students will make is they either won't factor by grouping correctly and thus be able to pull out front, and then they get lost right there, or they'll do everything right, and then when they get to this point, they'll forget their plus or minus. So don't forget your plus or minus. Factor by grouping, you ask what do they have in common? What do they have in common? The same thing should be inside your parentheses so that you can pull it out. Then you set each of these terms equal to 0 and you solve. Okay. Remember, if I go too fast at any point, you can always pause the video and go back and look through my notes as well, or rewind the video. So those are polynomial equations. The next type of equations that we are going to talk about are called radical equations. Radical equations are equations where the variable is under the square root or under the cube root or under the fourth root or so on and so forth. For this class, we mostly focus on square roots because if you can do the math with a square root problem, then you can do the same math with a cube root or higher problem. So the math doesn't change just because it becomes a different root. So when we are solving radical equations, the first thing you have to do is you have to isolate your radical to one side. That's standard pretty much for any type of problem we do where we're isolating the variable. And since the variable's under the radical, you're isolating the variable. So you isolate the radical to one side. If you have more than one radical, then you have to get them on opposite sides of the equal sign, which we're going to do one of each of these. After you've isolated your radical, you raise both sides to the nth power to eliminate that radical. So what that means is if our problem is a square root, to get rid of the square root, we square it. If our problem is a third root, then to get rid of the radical, we make everything to the third power, and so on and so forth. Now you keep doing those first two steps until you've eliminated all of your radicals. Once you've eliminated all your radicals, then you solve. Usually it's going to give you a quadratic formula or a quadratic equation. And so from the quadratic, then you can solve. Here's the important step. Check your solutions. I know most of our step-by-step processes list checking your solutions as the last step, but with radicals, you will have extra solutions called extraneous solutions. And that means that mathematically you got them, but when you plug them back in, they cause problems. I call them problem spots. So you see this a lot later on in the semester when it comes to holes in our graphs or asymptotes. And so that's what's going on here. So you have to check your solutions with radical equations, okay? Let's go work one. This one's the simpler of the two, where we only have one radical to start with. And it's right there on the bottom part of the notes as well, where we have the square root of 2x minus 1 plus 2 equals x. Step 1 says we have to isolate our radical. Well, it's not totally isolated yet because we have that plus 2. So I'm going to subtract 2 over. So I have the square root of 2x minus 1 equals x minus 2. Now my radical is isolated, and since it's a square root, I'm going to raise both sides to the second power. Remember, you do it on one side, you have to do it on the other. When you square a square root, that causes it to go away. So that'll leave me with 2x minus 1 on the left. But on the right, I'm going to have to FOIL in order to figure out what x minus 2 is squared. So 2x minus 1 equals, when you FOIL, you do first, which is x squared, outer, which is minus 2x, which I'm going to write really small right there, because then I have my inner, which is minus 2x, so that gives me a minus 4x. And then I have my last, which is negative 2 times negative 2, which gives me a positive 4. Since my x squared is positive already on the right side, I'm going to move everything over to the right side. So I'm going to subtract 2x and I'm going to add 1, subtract 2x and add 1. So I get 0 equals x squared minus 6x plus 5. This is a quadratic equation, just like what we had in 1.5. I'm going to rewrite it up here just so that you can see how I factor it. But I didn't do any math from this step to this step. I'm just simply rewriting it. There is a glare there, and I am sorry about that. So now we have a quadratic equation of x squared minus 6x plus 5, and we need to solve. The way we solve quadratics is we're going to factor. And when you're factoring quadratics, you can factor into the two sets of parentheses. First, I look at my first term, which is x squared. So I'm going to have an x and an x. Then you look at the sign in front of your c. That sign is positive. So that tells me both of my signs inside here are the same. I look at my sign in front of my b, and that tells me that both of my signs are negative. From there, it's actually really easy on this problem because 5 only has one factor, one set of factors, which is 5 and 1. So I just put those in there. If I FOILed this now, I would do x squared minus 5x minus 1x, which would give me my minus 6x, and then my negative 1 and my negative 5 would give me a positive 5. So I have factored this correctly. Now I do my zero product principle. So I set each of my terms equal to 0, and I solve. So x equals 1 and x equals 5. But here's the thing. I found my solutions, but I haven't checked them yet. And since this is a radical equation, I have to check my solutions. So what that means is I take those answers that I just got, and I'm going to plug them into the original problem and see if I get a problem spot or not. So anywhere in my original problem that I had an x, I'm going to put a 1. So I have 2 times x, so 2 times 1, minus 1, plus 2 equals x, which is 1. I'm testing my x equals 1. So I have the square root of 2 minus 1 plus 2 equals 1. Square root of 1 plus 2 equals 1. So I get 1 plus 2 equals 1. So I get 3 equals 1. Is that true? Does 3 equal 1? No, it does not. That means that x equals 1 is actually not a solution. It's called an extraneous solution. It's one that you get when you mathematically can solve it and you get that solution, but then you plug it back into the original equation and it doesn't hold true. So it's an extraneous solution. This is why you have to check. So let's check our 5 and see if it works. I wrote out the original problem. Anywhere there was an x, I put in 5. So 10 minus 1 plus 2 equals 5. Square root of 9 plus 2 equals 5. 3 plus 2 equals 5. 5 equals 5. Check. So my solution set is only 5. That is the only solution that works for this problem, which is all of that. So there's quite a bit of work because you have to isolate your radical, then you have to square both sides, which almost always is going to result in you having to FOIL. Then you have to move everything over, and then you have a quadratic equation, and then you have to solve the quadratic equation. So the nice thing is that you get a lot of practice working around with your quadratic equations, which is from chapter 1.5. So if you needed more practice, you definitely are going to get more practice with those in this section. So that one's the one that only has one radical, but like I said, if you have more than one radical, you can still solve. You just have to get the radicals on opposite sides of the equal sign. So let me get that problem put up for you. And actually I can scroll for you right here in the notes. So notice there's the problem, we check the solutions, there's the extraneous solution. I put a reminder there about perfect squares. It would save you foiling a little bit, but it's really not necessary that you have to do that. So right here is the next problem that I'm going to put on the board and work with you. This is the hardest radical problem that you will encounter. There is a radical problem that comes up on the final exam every year, whether it's the easy one or this longer one. It just depends. So it's definitely worth knowing how to do these. So we have the square root of 3x plus 1 minus the square root of x plus 4 equals 1. This is our problem. Step 1 says we need to isolate our radical, or if we have more than one radical, which we do, then we need to get them to opposite sides of the equal sign. Since this one's negative, I'm going to add it over to the other side. So I get square root of 3x plus 1 equals the square root of x plus 4 plus 1. Now that I have this radical isolated all by itself, I'm going to raise both sides to the second power to eliminate that square root. But if I square one side, I have to square the other side. Now squaring the square root eliminates that. That's because this square root is completely isolated. You cannot do that on this side. You cannot say, okay, well, I'm squaring a square root, so it's just going to be x plus 4 plus 1 over there. You can't do that because it's not isolated. Okay, so we're going to have to FOIL out this right-hand side. We can't just eliminate our x or our radical. So don't do that. I call that magic math. Okay, don't do magic math. It's not good. So over here, I'm going to write out x plus 4 plus 1 times the square root of x plus 4 plus 1. Just like I did on the problem a minute ago where I had x minus 2 squared and I wrote x minus 2 and x minus 2 and then we FOILed it. We're doing the exact same thing here, okay? So don't let the fact that this is a radical instead of just a simple x really confuse you, okay? So on the left, I have 3x plus 1. Now on the right, I'm going to FOIL. I do my first. So I have the square root of x plus 4 times the square root of x plus 4. Well, and I'll write it out the long way. That's the square root of x plus 4 squared. So notice that that's going to go away. This, then, the square does eliminate there. But I can do that in the next step. So that was my first. My outer is a plus square root of x plus 4. My inner is a plus square root of x plus 4. And my last is a plus 1. I still have 3x plus 1 on the left. I have the square root of x plus 4 squared. So I just have x plus 4. Then I have 2 of these square root of x plus 4s. So I have 2 square roots of x plus 4. And then I have a plus 1. So I have 3x plus 1 equals, and then I have x, and then I have a plus 4, and I have a plus 1, so that's plus 5, plus 2 square roots of x plus 4. Now, I have this long equation, but I only have one radical, so I get to treat it just like I did our first problem. I need to get this radical all by itself. In order to do that, I'm going to subtract x from both sides, and I'm going to subtract 5 from both sides. Okay, I'm going to tilt this just a tiny bit. So I had 3x minus x, that gives me 2x. And I had positive 1 minus 5, that gives me a minus 4, equals. And then the only thing left on this side is 2 square roots of x plus 4. I'm going to shift you down so that you can be right in front of where I'm at. Or as right in front as you can be. I guess you can be right in front. There. Okay. Nearly ready to do this one. We still have that 2 out in front, so we're going to divide everything by 2. Divide by 2. Divide by 2. 2x divided by 2 is x. Negative 4 divided by 2 is a minus 2. And then those go away, so I'm left with square root x plus 4. Now I have my radical completely isolated. So going back to step 2 then, I raise both sides to that power. I square both sides. Now this problem is almost exactly like our first problem, because I'll have x minus 2 and x minus 2. And then squaring a square root makes it go away, where I have an x plus 4 on the right. I have to FOIL. X squared minus 2x minus 2x will give me a minus 4x plus 4 equals x plus 4. Since my x squared is positive, I'm going to subtract my x and my 4 over. So subtract x, subtract 4. You get x squared minus 5x equals 0. Positive 4 minus 4 gives me no c on that side, and that's okay. I'm just going to rewrite this up here. I didn't do any math from this step to this step. I just copied it over. So now I have x squared minus 5x equals 0. I can't factor it in the traditional sense because I don't have my third term. So I'm just asking, what do they have in common? X squared and negative 5x both have an x in common. And that will leave me with an x minus 5 equals 0. Now I have a term times another term equals 0. So I can set each of my terms equal to 0 and solve. Luckily, that first one is already solved. So I just add 5, and I get 5. So my solution is 0 and 5, but we have to check. we can't just leave it because like we saw in our first one, there could be an extraneous solution. So we are going to check 0 and we're going to check 5. So the original problem, anywhere there's an x, I'm going to put a 0. We get the square root of 1 minus the square root of 4 equals 1. 1 minus 2 equals 1. Negative 1 equals 1. Is that true? Does negative 1 equal 1? No. That means 0 is an extraneous solution. So let's test 5 and see if it works. We have 3 times 5 plus 1 minus 5 plus 4 equals 1. 15 plus 1 minus the square root of 9. Square root of 16 minus 3 equals 1. 4 minus 3 equals 1. 1 equals 1. That's good. So our solution set is simply 5. Now I know the solution set for both of the examples we did were 5. That doesn't mean all of them have a solution set of 5. That's just the ones that I picked. So this problem is a lot. I mean, we used up 3 board spaces for this problem because you have to start by getting your square roots on the other side of each other. Then you square them, which means you have to FOIL. And then you have to isolate that new radical by itself. Then you square both sides, meaning you have to FOIL. And then you're going to have a quadratic, and then you have to solve the quadratic, and then you have to test your solutions. So it is a lot of work, and I understand that. The silver lining, as I like to look at it, is if you can do the big problem, the little problem is inside of it, and inside of the little problem is a quadratic problem. So you get lots of practice then on the little problem and on the quadratic problems. So this is a great place to really hammer in those details in that material so that you know it from here on out as we move forward. So that is the silver lining. If you like to look for the silver lining, hopefully you do. So there's the problem, and there's where I check it. There's an extra example in there as well if you'd like to work it. I even put the solution set over here on the side for you. This problem is a great way to test whether or not you've gained the knowledge from this problem because it works exactly the same way. The numbers are just changed. So I strongly recommend pausing the video and then working this extra example on your own paper and seeing if you get the correct solution set. And that way you know if you've gained the knowledge for that section. Okay, so we've done polynomials, we've done radicals, and now we're going to do rationals, equations with rational exponents, which actually ties in a lot with quadratics, or excuse me, not quadratics, with radicals, because you can rewrite radicals as rational exponents. If you see the word rational at any point in math, you need to think rational means fractions. So what this means is we have equations that have exponents that are fractions. And so I give a really general example right here where A is m over n, and that can be written as the nth root of A raised to the m power, or that can be written as the nth radical of A to the m. The way that I remember where my letters go or where my numbers go is this m on top of our exponent stays with your variable or stays with your number. A to the m over n. Notice you say the m first. So the m stays with your variable. The n is the one that comes out in front of our square root or our radical sign. Notice, see, it's the nth root and the nth root, and then the m is either in there with the a or it's just right outside. So That's how I remember it. Here is an example. We're going to do this example though, but if you want to see how we convert, we take the fourth root of x to the third. See how that third is connected to the x? So that's your top number. So it becomes x to the 3, and then the number out front pops down below and becomes the fourth. So x to the 3/4 is the same thing as saying the fourth root of x to the third. We're going to do this problem though and actually solve it. So I'll discuss that again here in just a minute. So when you solve, and it says radical, that's a mistake on my part. It needs to say rational equations. We have x to the m over n equals k. So what you want to do is you want to isolate the expression with the rational exponent. So you're getting x by itself. Step 1. Step 2 is you raise both sides to the reciprocal power. So you're going to flip your exponent and you raise both sides of your equations to that. Then you will solve and check your solutions. But there's one little caveat for this, is that you need to look at your m. If the m, which is the top number of your exponent, if the m is even, then you're going to have a plus or minus. When you raise it to that n over m power, you have plus or minus. If your m is odd, then you're just going to have the one solution. So if m is even, you get 2 solutions. If m is odd, you just get 1 solution. Okay? Let me erase the board behind me, and then we will do an example. Okay, we're going to do that example that's on the screen. That 3 times the fourth root of x to the third minus 6 equals 0. This is the problem we're going to solve. So the first step would be to convert this over into the rational exponents, or you can isolate it first. I kind of like to isolate it first because then I have less numbers over there to confuse me on what number is going where. So I'm going to add my 6 over. Then I'm going to divide both sides by 3. I'm completely isolating my x. That's what I want to do. So now I have the fourth root of x to the third equals 2. So remember, I said the top number of your exponent is the one that's with your variable. And then the number that was on bottom is the one out front. So what I usually think of is this number is the one coming around to go to the bottom. So it's x to the 3/4 equals 2. Now at this point, I have my x and it's to my rational exponent. So I'm going to ask, what is my m? The m is the top number. So in this case, my top number is 3. My top number is 3 means I have an odd m. And if I have an odd m, I have 1 solution. So I don't have to worry about doing the plus or minus in this case. I'm just going to get the 1 solution. So in order to get rid of this 3/4, I have to raise it to the reciprocal power. But if I do that on the left, I do it on the right. Here's why this works. When you raise a power to a power, you are multiplying those powers together. If I have 3/4 multiplied by 4/3, that gives me 12 over 12 because you multiply across. 12 over 12 is just 1, which leaves me with just an x. That's why we multiply by the, or we raise to the reciprocal power, is to just get x. And then over on the right, we have 2 to the 4/3. This is a totally fine, correct answer. You can leave it exactly like it is because it's the only one we have to do. If it asks for a decimal representation, then you would type it in, but you can leave it just like that. And that's the solution. And if I, excuse me, on my notes, if I scroll down, I do check my solution because it always, step 3 was check your solution. So I plugged it in and I got 3 times 2 minus 6 equals 0, 6 minus 6 equals 0, 0 equals 0, and that's it. So I know that my solution is a true solution and it holds. I'm just not doing that on the board. Okay, so that was one where M was odd. So obviously I'm going to do one where M is even and show you how that works. So it's down here at the bottom. I'm going to write it on the board as well. X to the 2/3 minus 3/4 equals minus 1/2. So this one's got a lot of fractions in it. If you are not totally comfortable with fractions, go back to chapter P. There's a whole section on fractions, how to add them, subtract them, multiply, divide them. There's also a section on exponents that could be helpful if you really don't like exponents. I do recommend doing that. So this one's already written with a rational exponent. So I need to isolate my x. And I'm going to do that by adding 3/4 over. Now I have 3/4 minus 1/2. So in order to combine those, I have to get a common denominator. My common denominator is going to be 4. And I get that by multiplying 1/2 by 2/2. That becomes 2/4. So x to the 2/3 equals 1/4, because 3/4 minus 2/4 equals 1/4. Now I'm going to raise both sides to the reciprocal power. So I'm going to raise both sides to the 3/2 power. And that gives me x equals, now, oh, I should have said it before. I'm so sorry. But my m was 2. 2 is even, which means I'm going to have 2 solutions. So as soon as I raise my, that, I'm going to write plus or minus, just so I don't forget that I'm actually getting 2 solutions. I have 1/4 to the 3/2. So what does that mean, 1/4 to the 3/2? Well, I'm going to come over here. Remember, the 3 stays with, and the 2 goes out front. So that would mean x equals plus or minus the square root of 1/4. And all of that is to the 3rd power. Remember, back up here with my a's, I can pull that power, that top number, outside and just do this on the inside. And for me, that's a lot easier in this case because the square root of 1/4, well, what's the square root, excuse me, of 1? Well, 1. And what's the square root of 4? 2. And then I have all of that squared. Well, 1, or cubed. 1 cubed is 1. 2 cubed is 8. So my solution set then is 1/8 and -1/8. So if you can simplify it out further, you always should simplify it out further. But if you can't, then you can't. But I kept working with it because I had a square root and I knew I could take the square root of 1/4. I knew I had a square root because I had a 2 in the denominator of my exponent. So I kept working it and kept working it and kept working it. Okay. So those are equations with rational exponents. I know those are not probably your favorite. And the good news is we don't do a whole bunch with them, so you're not going to see them a whole bunch. So let's move on to the last style of equation that we're going to have today, which is equations with absolute values. So remember, before we talk about these, that absolute values tell you how far away from zero a number is. So I give you an example that the absolute value of 2 equals 2 because it's 2 places away from 0 on our number line. And the absolute value of -2 is also 2 because it is 2 places away from 0 on the number line. It's just on the left-hand side of the 0 instead of the right. So that's what absolute values are. Now we can start solving absolute value equations. And especially compared to these last two types of equations, I bet you're going to like them a lot. Okay, so how do we solve absolute value equations? Well, let's look at an example. Absolute value of 2x minus 3 equals 11. So like I just showed you, the absolute value of 2 was 2, and the absolute value of -2 was also 2. So what was inside of our radical could have been positive or negative to get us that solution. So when we solve absolute value problems, let me scoot you over a little bit. When we solve absolute value problems, what we're doing is we're going to split it into two different problems. We're going to have a positive one and a negative one. So I'm going to write what's inside of my absolute value, 2x minus 3, and that equals 11. This will be my positive one. Then I will write 2x minus 3 equals -11. This will be my negative equation or my negative solution. Now we just solved both of these equations. So 2x minus 3 equals 11. I'm going to add 3 to both sides. We're at 2x equals 14. Divide both sides by 2, and I get x equals 7. Over here, I'm going to add 3 to both sides, so I get 2x equals -8. Divide both sides by 2, and I get x equals -4. So my solution set would be -4, 7. Much easier and much more straightforward than our radical and rational equations. So for absolute values, you split it. We have a positive one and we have a negative one. And notice I checked my answers. I plugged in 7. That gives me 14 minus 3, which gives me 11, which is 11. Over here, I plug in -4. That gives me -8 minus 3, which gives me -11. This absolute value of -11 is +11. That's why we split it. Notice what's in our absolute value stays exactly the same for both of the equations that we solve. We just put a negative in front of our answer when we split. Okay, let's do another one. Just because I've been working 2 examples of every single style of problem. Let's do 5 times the absolute value of 1 minus 4x, absolute value minus 15 equals 0. Okay, we don't want to split yet into 2 different equations because we don't have our absolute value by itself. So get your absolute value completely by itself before you split. So I'm going to add 15 to both sides. Now I still have this 5 out front, so I'm going to divide both sides by 5. Now I have the absolute value of 1 minus 4x equals 3, so I can split now. I can have 1 minus 4x equals 3, 1 minus 4x equals a -3. I'm going to subtract 1 over. Divide both sides by -4. -2 over 4 simplifies down into -1/2. Over on this right equation, I'm going to subtract my my 1 over, which gives me -4. Divide both sides by -4, and I get x equals 1. So my solution set is -1/2, 1. Notice on the notes, I do check both of those solutions to make sure that they are accurate and they do both work. So the absolute value problems are the nicest and the easiest ones out of the ones we are working on today. But don't let the other ones scare you away. Practice, practice, practice. On the homework, you can do the problems over and over and over again. When you complete a problem and if it's one that's really tripping you up, you can select in the bottom right-hand corner will be a similar exercise button. That button will regenerate the problem with the exact same process. It'll just have different numbers. So like in this case, it would say 6 and then 3 minus 2x minus 24 equals 0 instead of what it has. It has the exact same steps. It'll just have different numbers. So that is section 1.6, and that is the end of this.